Hello, this is the presentation on section 15.2, solution concentration. You'll need a calculator. We're going to be doing a number of calculator problems. You'll also want to have your periodic tables out so you can look up some molar masses. Start off with some trivia. Here's an abbreviation for a phrase of some sort. There's going to be a number of them, so I'll give you what the first one is. 52 equals C in a D, WJ. 52 cards in a deck with jokers. I'll pop the other ones up here, and you can pause the video if you want and try to figure them out yourselves. Molarity. Molarity is a measure of the concentration of something, of a solution. In this case, molarity will be moles of the solute over liters of solution. That's going to be our formal definition. It's going to be our equation that we're going to be using. When you have it written, it's going to look something like this, 6MHCl, which represents 6 molar hydrochloric acid solution. Just gives you the concentration. The larger the number, the more concentrated it is. Just like when you make Kool-Aid. The more sugar you put in, the more concentrated the sugar is, the sweeter it's going to be. Same thing with chemistry here. Let's take a look at a problem from your book, page 465, number 15. What is the molarity of a bleach solution containing 9.5 grams of sodium hypochlorite in a liter of bleach? Remember our formula, molarity, capital M. That's molarity utilizes the capital M is equal to N moles over L. That's going to be our liters of solution. We're looking for the molarity. So the first thing we need to do is calculate the N. That's going to be moles. We're given grams of this material, NaOCl. We need to figure out how many moles that is. So we'll need to calculate the molar mass of NaOCl. And we get 74.5 grams. That's going to be 1 mole with 1 mole in the numerator. So our grams will cancel out, and we will end up with moles of NaOCl. And now we can plug it into our formula. Our original formula, molarity is equal to moles over liters. We have moles now. We know that we're talking a liter of bleach. So we divide it by 1 liter here, and we get 0.128 molar. That's our concentration, 0.128 molar bleach. Let's work another practice problem. Calculate the molarity of a 1.6 liter solution containing 1.55 grams of dissolved KBr. So let's take a look at that. If you want to pause the video right now, you can try to work this problem out yourselves. Remember, we need to look at molarity is equal to moles over liters. We have the liters. We're given that. We need to figure out moles. We're given grams. Again, we need to convert from grams to moles. N is equal to 1.55 grams of KBr. Then we'll do our parentheses line, grams KBr in the denominator, moles in the numerator of KBr. We know that that's going to be 1 mole in the numerator, and then we're going to have the molar mass of KBr. That's going to be 119.0. There's going to be our molar mass. Grams KBr will cancel, and we will end up with 0.013 moles of KBr. So that's going to be our N. Now we know what N is, we know what L is. Molarity is equal to N over L. It will be equal to 0.013 moles KBr over our liters, 1.60 liters KBr. And we will end up with .0081 molar for our answer. We need that units of capital M, molarity. And that's how we do these problems, calculating the molarity of a solution. Preparing molar solutions. This is what I do on a weekly basis. A lot of the solutions that we're working with in the labs are not solutions originally, they are solids. A lot of them are going to be ionic compounds, which typically will be in solid form. And so I need to add some water to them to make a certain concentrated solution, depending on the experiment that we do. We know that molarity is equal to moles of the solute over liters of solution. We just finished doing that. We can rearrange this. We can solve for moles of solute. If we want to solve for moles of solute, we will be given molarity and liters of solution. Because whenever I make a solution, I know how much I need to make, whether it's 500 milliliters, 1 liter, whatever it is, and I'll know the concentration. I know that to begin with because I know what we need for the experiments. But I need to figure out how much of the solute, how much of that solid material I need to begin with. So this is how I do it. Let's take a look at a practice problem. How many grams of calcium chloride would be dissolved in 1 liter of a 0.1 molar solution of calcium chloride? Another way to say this is how many grams of calcium chloride do I need to make a 1 mole, or to make 1 liter of a 0.1 molar solution. That's another way to write it, another way to say it. We have our formula. N is equal to capital M times L, which we just saw there, just rearrangement of the formula. Molarity is equal to N over L. Just rearranging it, solving for N. This time, if we want to solve for N, that's what we need to do. And we plug our numbers in. We know what the molarity is. We're given that. This is going to be our M. This is going to be our L. We're given that in liters. Calculate, do the calculations, and we end up with 0.1 moles. That's going to be calcium chloride. If we have the moles of calcium chloride, we can easily figure out grams of calcium chloride. Again, just our standard mole conversion problem. Going from moles to grams this time. We need to have grams in the numerator and moles of calcium chloride in the denominator. This, of course, is going to be 1 mole of calcium chloride. Our units calcium chloride, moles of calcium chloride will cancel out. So we'll end up with our 0.1 moles times 111 grams, and we will end up with 11 grams of calcium chloride. So if I need to make the solution 1 liter, if I need to make 1 liter of a 0.1 molar solution of calcium chloride, I need to add 11 grams to my container and then dilute the rest of it with water. Let's work another practice problem. Here it is in your books. If you want to stop the video now and practice it yourself, you can do that. I'd recommend doing that to give you a little bit of practice. It says a liter of 2 molar sodium hydroxide solution contains how many grams of sodium hydroxide? So we have our givens. This is our volume in liters. So we have our liters, which is 1. We have our molarity, which is going to be 2. So we just plug it into our formula. We know that moles is equal to molarity times liters. Again, remember this molarity is moles over liters. So when we take moles over liters times liters, the liters will cancel and we'll end up with moles. So that's what we're looking for. So now we can just plug these numbers in. The molarity is equal to 2. It's going to be 2 molar times 1 liter, and that's going to give us 2 moles. So we have 2 moles of sodium hydroxide. We need to figure out grams because that's what the Problem states how many grams. So we have 2 moles of NaOH, parentheses line, mole NaOH in the denominator, grams NaOH in the numerator. When we plug in our numbers here, doing mole conversions, it's always going to be 1 mole. We need the molar mass of NaOH, 40.0 grams of NaOH. And we do our calculating. 2 times 40 divided by 1, and we get 80.0 grams of NaOH for our answer. So if I want to make up a liter of 2 molar sodium hydroxide solution, I would need 80.0 grams of it. So I take 80.0 grams, put it in my container, add enough water to give me exactly 1 liter, mix it up, dissolve everything, and I am set to go. So that ends the first part of this video. The second part talks about making dilutions. Making dilutions is when you have a concentrated solution and you need to dissolve it, or you need to dilute it down a little bit. If you accidentally added too much sugar to your Kool-Aid, it's going to be too sweet. You're going to need to dilute it down. Whenever I make solutions, sometimes I make very concentrated solutions, a small amount of that, and then I can use that to make more material at different concentrations. So remember, molarity is equal to moles over liters. That's our original definition. When we dilute something, the number of moles in that container, in that solution that we have, will remain the same. Kool-Aid example again. If you have 2 cups of sugar in 2 quarts of water, if you take another 2 quarts of water, put it in there, you still have your original 2 cups of sugar in there. The amount of sugar has not changed. The concentration has changed, but not the amount. So that N is always going to be the same. It never changes. So the moles of solute, again, is molarity times liters of solution. Just rearranging our equation again, just like we did when we were making our molar concentration, or molar solutions. And since this moles of solute will always be the same, it's never going to change, we know that our original molarity times the volume that we had is going to be equal to our final molarity times our final volume, because they're going to be the same. If we have some concentrated Kool-Aid here, when we dilute it down, we are going to increase the volume of that because we're adding more water to it, but we're going to decrease the molarity because the concentration is going to go down. So this is our formula equation. Looks very much like Boyle's law, which we just covered with the gas laws. Do it the exact same way. Let's take a look at a practice problem. What volume of a 3.00 molar Ki stock solution? Again, the stock solution is what you make up originally at a very high concentration. So when you dilute it down, you can dilute it down into different concentrations. If you need different concentrations, easy just to make one stock solution and dilute it down from there. How much would you use to make 0.3 liters of a 1.25 molar Ki solution? Again, the whole key is to identify your knowns and unknowns, just like the gas laws. You must do that. Question is, what volume? So you can set your V1 is equal to question mark of a 3 molar stock solution. You know that these two go together. What we're looking for in 3 molar, because it says what volume of A, that goes together. So that has to be your M1 and V1. Could be your M2 and V2. They just have to be together. If you would be used to make, so what you're looking to make is a 0.300 liters. That's going to be your final volume. And your final concentration will be 1.25 molar. So now you have your numbers. Write down your formula and just plug it in from there. Your M1 is going to be 3.00 molar times your V1. That's going to equal your M2, 1.25 molar, times V2, 0.300 liters. Going to be solving for V1, so you just divide by 3.00 molar, 3.00 molar on both sides. Your units, units of molar cancel out. This liter still stays there. And you get, what you're going to be doing is taking your 1.25 times 0.300 divided by 3.00, and you will end up with your final answer of 0.125 liters. A lot of times we don't use liters in the lab. We have graduated cylinders and things that measure things in milliliters. We can convert this to milliliters by just moving in the decimal place over 3 places to the right. Since milliliters, there's 1,000 milliliters in a liter. If you move it to the right 3 places, we get the right number, 125 milliliters for our final answer. So if we want to make up that solution, we take 125 milliliters of our stock solution, we put it in a container, and we add enough material, enough water, until we reach 0.3 liters or 300 milliliters, and we are set to go. Then there we have our solution. Let's take a look at another practice problem. You can try to figure this one out. Again, stop the video and go on, try to figure this one out yourselves. It says how many milliliters V1 is equal to question mark of a 5.0 molar solution. M1 is equal to 5.0 molar. And it says is needed to prepare 100 milliliters. Volume 2 is 100 milliliters. And our molarity 2 will be, number right here, 0.25 molar. So again, you have to keep your M1 and V1s together, V2 and M2s together in order to do it correctly. We know that M1 V1 is equal to M2 V2. Now we just need to plug the numbers in. M1 is 5.0 molar times V1 is equal to M2, which is our 0.25 molar, times 100 milliliters. Solving for V1, divide both sides by 5.0 molar. Our molar units will cancel, and we will end up with 0.25 times 100 divided by 5.0, and we will end up with 5.0 milliliters. You should always check your answer. One way to check your answer is to look at your answer, your 5.0 milliliters, and then look back at how much you are going to be producing. How much do you want? In this case, we want 100 milliliters. If we want to make 100 milliliters, it says that we need to add 5 milliliters of this stuff. That makes sense. If you get an answer, and some of you will when you work these problems, if you get an answer that calls for, let's say, 250 milliliters, so let's say that's your answer. That's wrong, because you cannot use 250 milliliters in order to make 100 milliliters. It's impossible. You can't do that. So check your answer. Make sure that your answer makes sense. You'll need less material than what you're actually going to make. So it's a good way to check the answer. One last thing, lab coming up on Friday. This is the first question. Same type of a problem. We'll do it right here. This says, how many grams of copper chloride dihydrate would you need to make a 0.3 molar solution in a 100 milliliter volumetric flask? Remember, when you're doing a problem like this, you're looking for how many grams of that material, so we need to figure out how many moles of this copper 2 chloride dihydrate we will need. So moles is equal to molarity times liters. We know what our molarity is. We know that this is big M right there. We know that our volume is right here. So we have those numbers. We need to change this milliliters into liters. 3 places to the left will give us liters for our units. We can plug these numbers in. Our molarity times liters, we know molarity is 0.30 molar. We know our volume is 0.1 liters. When we do that calculation, we get 0.03 moles of our copper 2 chloride dihydrate. We don't need moles. What we're looking for is grams. So when you calculate that out, you're given moles of copper 2 chloride dihydrate, 2H2O. We need to put moles in the denominator. And we need grams in the numerator. We know that 1 mole of copper 2 chloride dihydrate is going to be the molar mass of this whole thing. The molar mass, we need this whole thing. We need 1 copper, we need 2 chlorines, and we need 2 waters associated with it. When you do that, you get 170.5 for our molar mass. Doing the calculations, 0.03 times our 170.5 divided by 1, and we will end up with 5.12 grams of CuCl2.2H2O for our final answer. A lot of calculations going on here. Make sure to know how to do these. I've done a couple of examples of each type for you. Whole key is to figure out which formula to use. For this formula we just did here, you're going to be given a volume and a molarity, and you're going to be calculating grams or moles. When you're calculating grams and moles, this is the formula to use. The other ones, you'll be given, for the dilution problems, you'll be given a volume, a final volume, and a final molarity, and you'll be given an initial molarity. So you'll be given 2 molarities and a volume. When you're given that, you know it's going to be a dilution problem. And that concludes our presentation. Hopefully you found this helpful.